Namaste viewers, welcome back to my channel. In this session I am going to discuss Laplace transforms. Transformation is one of the most important tool to solve the differential equations in electric engineering problems. Okay, like to solve the ordinary differential equation or partial differential equation. To solve the solutions of differential equation, it plays a most important role. Okay, and this is the one of the most important topic we use in various topics in mathematics. Okay, in various branches in mathematics. Okay, in this session I am going to discuss very basic to advanced levels of Laplace transformation. Okay, welcome to my channel. My name is Akshay. Okay, this is the introduction. Pause the video and read this introduction. Now I am going to start with the definition of Laplace transform. Okay, let f of t be the function of the variable t which is defined for all positive values of t. Let s be the real constant. The integration 0 to infinity e raised to the power of minus st f of t dt exists and is equal to f of s, then f of s is called the Laplace transform of f of t and it is denoted by L of f of t. Okay, this is the important one. Laplace transform definition. L of f of t is equal to integration 0 to infinity e raised to the power of minus st f of t dt is equal to f of s. Okay, this is the definition for Laplace transformation. Here L is called as the Laplace transform operator. Okay, this is the most important one. And the another definition is piecewise continuous function. Piecewise continuous function, a function f of t is said to be piecewise continuous in any interval, okay, closed interval a comma b, if it is defined on that interval and the interval can be divided into a finite number of subintervals in each of which f of t is continuous. Okay, otherwise we can say other definition also. In other words, piecewise continuous means f of t can have only finite number of discontinuous. For example, suppose if you consider a interval, suppose if you consider it is t, it is f of t. For example, if you consider some interval, finite interval a b, okay, this finite interval is divided into some subintervals, for example t1, t2, t3, t4. Okay, now in these subintervals the function must and should continuous, okay, except these points. Okay, in these each interval, in these each subinterval the continuous should be, sorry, the function should be continuous. Okay, otherwise we can say that throughout this interval the function is continuous except at these intervals, sorry, except at these points. Okay, t1, t2, t3, t4, at these points the function is not continuous, function f of t is discontinuous. Okay, then we say that it is a piecewise continuous function. Okay, for example, if you look at this diagram, look at this graph. If you consider a finite interval alpha beta, it is divided into some subintervals t1, t2, t3. We know that what is the graphical definition of continuous function. If you draw the any graph without lifting a pen, okay, it is the graph this graphical method of continuous function. Okay, if you want to draw any continuous function without lifting a pen or pencil. Okay, for example, see, if you observe that this interval, you draw the graph without lifting the pen. Okay, here see. Okay, but at this point t1, when you need to lift the pen and again start here. Okay, right, is continuous. In this interval in between t1 and t2, the graph is continuous. Okay, the function is continuous. Here also in between alpha and t1, the function is continuous, but again you need to lift the pen and again you need to start here. Okay, here also the graph is continuous. Okay, and again you need to lift the pen and you start here. Here also in between t1 and t3 and beta, the graph is continuous. Okay, that means at the points t1, t2, t3, except at these points, throughout throughout this interval alpha beta, the graph is continuous except at these points t1, t2, t3. Okay, that means the function is discontinuous at t1, t2 and t3. Then we say that this f of t is piecewise continuous. Okay, otherwise we say that this is piecewise continuous graph. Piecewise continuous graph. Okay, and definition of exponential order. Okay, a function f of t is said to be exponential order if limit t tends to infinity e raised to power minus st f of t is equal to 0. Okay, if this condition is satisfied, then we say that the function f of t is a exponential order. Okay, and this is the most important, the sufficient condition for the existence of the Laplace transforms. Okay, let f of t be defined and continuous for all positive values of t. The Laplace transform f of t exists if the following conditions are satisfied. The first condition is f of t is piecewise continuous, and second condition is f of t should be exponential order. Okay, this is the two important conditions. These are the two important um, conditions for existence of the Laplace transform function. Okay, and we're going to discuss some examples. Okay, to solve this example we need to know some indeterminate forms. Okay, 7 indeterminate form. Okay, whenever these indeterminate forms occurs, we cannot solve the limits directly. Okay, for this type of limits we need to apply some methods. Okay, for 0 by 0, infinity by infinity, 0 into infinity, infinity into infinity, 1 raised to power of infinity, infinity raised to power of 0, 0 raised to power of 0. These are the 7 indeterminate forms. Okay, to solve 0 by 0, infinity by infinity, we can use the L'Hospital rule. L'Hospital rule to solve 0 by 0 or infinity by infinity forms. Okay, first solve 0 into infinity and infinity into infinity. We need to convert these indeterminate form into 0 by 0 or infinity by infinity. Okay, then apply L'Hospital rule. Okay, for 5th, 6th and 7th indeterminate forms, we need to take log on both sides. Okay, then we need to simplify it. Okay, this is the method to solve this indeterminate forms. Okay, we need to check exponential order for these examples. check whether the following functions are exponential or not. Okay, the first one is f of t is equal to t square. F of t is equal to t square. What is the definition for exponential order? Limit t tends to infinity e raised to the power of minus st into f of t. This should be equal to 0. If you get this equal to 0, then we say that this function is exponential order. Okay, first rewrite this one. T tends to infinity, just we need to take this into denominator. We get like this, e raised to the power of st. And what is f of t? F of t is t square. Okay, now applying limit in place of t, okay, we get infinity by infinity form. Then applying the L'Hospital rule, or we say this as L'Hospital rule also. Okay, pronunciation. The L'Hospital rule say that we need to differentiate numerator and denominator separately, okay, with respect to t. Okay, the differentiation of t square is what? 2t. Okay, and the differentiation of e raised to the power of st is e raised to the power of st, and again chain rule, applying chain rule, we get s here. Okay, here we applying the limit for only t, that's why we take 2 by s outside. We get limit t approaching to infinity, t by e raised to the power of st. Okay, again if you apply the limit, we get infinity by infinity form. Okay, again we get infinity by infinity form. Then again applying the L'Hospital rule, we get differentiation of t is 1 e raised to the power of st into s. We get this is 2 by s square, and limit t approaching to infinity, 1 by e raised to the power of st. This is 2 by s square. Applying the limit, we get 1 by infinity. 1 by infinity value is 0. Okay, 2 by s square into 0 value is 0. That means we get limit t in t tends to infinity e raised to the power of minus st, f of t equal to 0. Then we say that f of t is equal to t square is exponential order. Okay, see, it's exponential order, and we can check same like this. F of t is equal to e raised to the power of t square by the definition of exponential order. Okay, if you simplifying this, we get this as infinity. Okay, then f of t is equal to e raised to the power of t square is not a exponential order. Okay.